trace elements in the environment, perspectives from the swamp laboratory. I'm the Bocock Chair for Agriculture and the Environment at the University of Alberta. So there's two parts to my presentation. The first part is background to our study and some of our published findings. So a little bit of background, just very briefly. The focus of my research are potentially toxic heavy metals. And these are the elements shown here in red. Elements like silver and cadmium and thallium and lead and antimony and arsenic, these have no physiological function, so they cannot be beneficial to living organisms under any circumstances. So these are potentially toxic so-called heavy metals. And if we look at the abundance of elements in the Earth's crust, what we see is that these elements occur in the Earth's crust at very low concentrations. So very low concentrations in the Earth's crust means low concentrations in soils, it means low concentrations in plants, and it means very low concentrations in water. And so that's why we need a clean laboratory to study these elements in the environment. So objectives of our studies on the lower Athabasca. So we're interested in quantifying and characterizing atmospheric emissions. So we want to know how much of these elements are being emitted to the environment from open pit bitumen mining, from upgrading, and also what forms are these elements in, because elements can be found in many different forms. We also study aquatic emissions. So what is ending up in the Athabasca River? And this photograph shows you a bitumen outcrop. There's probably about 35 massive bitumen outcrops between Fort McMurray and the Firebag River. So in our research, again, focus is elements like silver, cadmium, lead, antimony, thallium, these potentially toxic elements. We want to know what is being supplied to the air and to the water from industry, the anthropogenic input. But really, to understand the anthropogenic input, we have to understand the natural inputs. Okay, so what is the natural abundance? What are the natural forms, the natural fluxes? So the swamp laboratory at the University of Alberta is a metal-free, ultra-clean research facility. So this entire facility was designed and constructed specifically for looking at trace elements in soil and water and air and plant materials. So the whole lab is built of plastic, all of the air is filtered, very sensitive analytical tools. We can measure trace elements down to extremely low concentrations. So to summarize our work on atmospheric deposition, we use moss as a monitor, as a natural monitoring tool to look at contemporary atmospheric deposition. So this is sphagnum moss that you find in peat bogs, very cool little plant. Okay, it's growing at one end, it's dying at the other. It does not have any roots. So the elements that you find in this plant were taken up from the air. So if we analyze the plant, we get an idea what is in the air. And certainly when we look at the amount of mineral material or the amount of dust particles on the plants near the open pit mines and near the upgraders, we certainly have elevated amounts of dust on the plant surface, as you can expect. Okay, so we collect moss all around these open pit mines and upgraders, measure the amount of ash, and it gives us an indication of how much dust is being supplied. And because we know the rate of plant growth, we can determine the rate of dust deposition. So it's certainly a dusty area near the mines. And this is some work by Gillian Moulin-Boudreau, and she looked at these plant surfaces with the scanning electron microscope, and you can see there's relatively large, the scale bar here, 20 microns, relatively large dust particles on the surface of the plants. So this work has been published in Environmental Science and Technology. So if anybody wants a copy of that publication, just send me an email. In terms of potentially toxic heavy metals, we've looked at all of the relevant ones. Lead, for example, the concentrations of lead in the plants are low, and the concentrations of lead are proportional to the amount of thorium. And thorium is a metal that indicates the abundance of dust particles. So those arrows that you see at the bottom, Earth's crust, the red arrow at the top, soil, if you look at the ratio of lead to thorium in our moss samples, it's what you would expect based on the ratio of lead to thorium in rocks and in soils. So the lead concentrations are low, and the variation in lead reflects a variation in the amount of dust particles. And similar results for silver and cadmium and antimony and thallium. So we did publish this paper back in 2014 in Environmental Science and Technology. In the sphagnum moss, we see no significant atmospheric contamination by heavy metals. We've also looked at snow in the area, and you can see in that top slide, JPH4, you can see some brown bands. These are dust particles in the snow. And Dr. Javed did the study of the composition of these particles. And if you look at the amount of lead that's in these particles, again, it's proportional to the amount of thorium that's in the particles. So lead concentrations in the snow are almost exclusively in the dust particles, and the amount of lead is what you would expect based on the amount of thorium in the dust. And this work has also been published if people are interested in that. And the amount of lead that's in the dissolved fraction of the snow, if I can say it that way, is extremely, extremely low. Now, peat bogs are really cool where this moss is found because they allow us to reconstruct the history of atmospheric deposition. And these are peat cores. These are 6 bogs, different distances from the oil sands industry. And what's shown on the y-axis is the calendar year. So we've developed methods for dating the peat cores. And we see the lead enrichment in all of these cores reached its maximum value in the past, and lead in the air has been in decline for decades. So this peat bog information is showing us that the extent of enrichment of lead in the air is in decline. And this paper also published, peat bogs in northern Alberta revealed decades of declining atmospheric lead contamination. And if we look at the other potentially toxic heavy metals, we see a very similar story. So here's a graph showing cadmium concentrations, our 6 peat profiles, and at the top of these profiles, we have the same cadmium concentrations. And the maximum, so they're independent of distance from the mines, the maximum amount of cadmium in these peat profiles, again, was in the past. So we published this paper in ES&T, peat bogs document decades of declining atmospheric contamination by trace metals. In terms of our work on water, we've collected water samples using our small boat, starting out upstream of Fort McMurray, going downstream, past the open pit mines and upgraders. And as we go far downstream, well past industry, we see this pink color in the river. That's terrain conductivity, which is proportional to the salinity of the water. So as we go downstream in the river, there's inputs of saline groundwaters. And in our team, we're trying to understand what is the contribution of those saline groundwaters to the chemistry of the water. So starting with the dissolved concentrations of trace metals in the water, So we filter the samples very carefully. We use clean bottles, clean filters, clean syringes, clean lab clothing. We filter the water to remove the particles because we want to measure what's in the dissolved fraction. So here's an example of a filter, 0.45 microns, collecting particles. What passes through the filter, in the past, we've considered that dissolved. Okay, if we look at dissolved lead in the Athabasca River, on the left-hand side upstream, the right-hand side downstream, the concentrations upstream and downstream are not significantly different. The lead concentrations are low, and they're comparable to the natural background values for lead dissolved in other uncontaminated rivers. Cadmium concentrations very low, antimony concentrations very low, same thing with thallium. So silver, cadmium, lead, antimony, thallium, they are not significantly more abundant downstream of industry compared to upstream. And again, I'm talking about dissolved in the water. And this work also has been published. I just want to mention that all of that work was done on our small ICP mass spec, but all of our data was confirmed using our large ICP-MS, our sector field ICP-MS, which was operated by Dr. Bicalho. So our data, we double check, we triple check, we will check as many times as we need to be absolutely confident in our results. Now, truly dissolved concentrations, these are things that are smaller than a nanometer. So when we filter our water sample, even though in the past we considered that the dissolved fraction, we now know that the dissolved fraction is in a much smaller size fraction. So Chad Cuss is the guru of this technology, flow field, flow fractionation combined to ICP-MS. This is a way to measure trace metals as a function of the size of the molecules, specifically as the size of the colloids. And Chad has published this beautiful paper in Analytical Chemistry explaining how we do this separation and measure trace elements in those colloids, which are the particles that are so small they actually pass through the filter. In the case of iron, okay, we have relatively large colloids, so 150, 250 nanometers, and most of the lead that's in this so-called dissolved fraction is actually associated with these iron particles. And a small amount of the lead is also associated with organic molecules that are even smaller. They're between sort of half a nanometer and 5 nanometers. We've also looked at arsenic in the water, and this is the work by Mark Donner, part of his PhD thesis. And you see a transect from upstream to downstream. Dissolved arsenic in the Athabasca River is low, and it's not significantly more abundant downstream from industry compared to upstream. This is his data from 2014. We went out the following year, redid all of the sampling, and the results are virtually identical. And Mark's work has been published, and it's one of the nicest papers I've ever seen on arsenic speciation in rivers. So how to explain all of the results that I've just shown you? It's actually very simple. The answer lies in the Athabasca bituminous sand itself. Okay, if we take the sand and we extract the bitumen using organic solvents and we analyze the bitumen, we find only 4 metals: vanadium, nickel, molybdenum, and rhenium. All of the other elements, so the potentially toxic heavy metals, they're in the mineral fraction. In other words, they're in the sand fraction. They're hosted in the minerals that make up the sand. And those minerals should be relatively insoluble. And this work also has been published. So the trace element concentrations, the potentially toxic heavy metals in the sand fraction of the Athabasca bituminous sand, the abundance of those elements in that sand fraction is going to be no different than the abundance of the elements in this beach sand from my favorite beach on Lake Huron near Elmvale, Ontario. Thank you very much for your attention, and we'll be back in part 2.